Now, let us consider another problem as per which there is a LTI system whose system function is given as h of z and impulse response is given as h of n. It's also given that in case of the impulse response, h of 2 is equal to 1 and h of 3 is equal to minus 1 and h of k is equal to 0 otherwise. There are two statements given as related to the LTI system saying that it's a low pass filter and it's a FIR filter. We need to pick or we need to mark if the above two statements are correct or not. The impulse response of the LTI system can be given as h of n is equal to 0 comma 0 comma 1 comma minus 1 sorry 0 comma 0 comma 0 comma 1 comma minus 1 where the value of first 0 corresponds to the instant n is equal to 0. Upon finding the DTFT of the h of n, we get that h of e power j omega is equal to e power minus 2j omega plus e power minus 3j omega. This is equal to e power minus 2j omega multiplied by 1 plus e power minus j omega. This can further be simplified as e power minus 2j omega multiplied by 1 plus cos omega minus j sin omega. Upon finding abs of h of e power j omega, we see that the magnitude of e power minus 2j omega is 1, which is multiplied by abs of 1 plus cos omega minus j sin omega. This is equal to square root of 1 plus cos omega whole square plus sin square omega. We know that 1 plus cos omega can be written as 2 cos square omega by 2 and sin omega can be written as 2 sin omega by 2 cos omega by 2. Upon substitution and by using the trigonometry properties, we see that abs of h of e power j omega is equal to 2 cos omega by 2. Upon plotting this, we see that abs of h of e power j omega looks as shown. It has a value of 0 at pi and minus pi and it has a value of 2 at omega equal to 0. From this we see that the given LTI system passes low frequencies and attenuates high frequencies. From this we can say that the given system is low pass filter. So the statement 1 is correct. Also from the given impulse response we see that the length of the impulse response is finite. From this we can say that it is a FIR filter. Sorry, please note that the impulse response is 1 comma h of 2 is 1 and h of 3 is also 1. So that's how we solved for h of e power j omega and abs of h of e power j omega. So from this we can say that the given filter is LPF and also the given filter is FIR. From this we can say that the statements 1 and 2 are correct. Now let us consider another problem as per which it is given that there is a linear phase system whose impulse response h of n is real. It is given that 1 0 of the linear phase filter system is located at 1 by 2 multiplied by e power j pi by 4. We need to find the location of the other zeros. From the given data, we see that in case of a linear phase system with real impulse response, if there is a zero at j, z, then there is another zero located at z star because the zeros are complex conjugates as impulse response is real. From this, we can also say that as the system is linear phase, zeros form conjugate reciprocal pairs. So definitely we can say that there exists a zero at 1 by z star and 1 by z star whole star, that is equal to 1 by z. So finally we can say that there are zeros located at z, z star, 1 by z star and 1 by z. So from this we can say that the location of the zeros is 1 by 2 e power minus j pi by 4, which is z star, and 1 by 1 by 2 e power minus j pi by 4. This is equal to 2 power a j pi by 4. This corresponds to 1 by z star, and there is another 0 at 2 into e power minus j pi by 4, which corresponds to 1 by z. From this we can say that the given linear phase system with real impulse response has zeros at half e power minus j pi by 4, 2 into e power j pi by 4 and 2 into e power minus j pi by 4. Now let us look into another problem as per which there is a discrete time signal x of n given as 1 comma 0 comma 2 comma 3, where the value of 1 corresponds to the first corresponds to n is equal to 0. We need to find the 4-point DFT of the signal. Here the signal x of n is of length 4. From this we can write that omega n is equal to e power j 2 pi by n, which can be simplified as e power j pi by 2. From this, the 4-point DFT can be written as x of k is equal to sigma n equal to 0 to n minus 1 x of n multiplied by omega n power minus kn, which can be simplified as x of 0 multiplied by e power minus j0 plus x of 1 multiplied by e power minus j pi by 2 plus x of 2 multiplied by e power minus j pi plus x of 3 multiplied by e power minus j 3 pi by 2. Upon substituting the values, there should be k here. Upon substituting the values of x of n, we see that x of k is equal to 1 plus the second term would be 0 because x of 1 is 0, 2 plus 2 multiplied by e power minus j pi k plus 3 multiplied by e power minus j 3 pi by 2 k. From this we see that if k is equal to 0, x of 0 would be equal to 6. If k is equal to 1, x of 1 is equal to 1 plus 2 into e power minus j pi plus 3 into e power minus j 3 pi by 2, which upon simplification becomes 1 minus 2 because e power minus j pi is equal to minus 1 plus 3 into e power minus j 3 pi by 2. Here e power minus j into 3 pi by 2 can be written as j. Upon substituting the same, we see that the value is equal to minus 1 plus 3j. Similarly, for k equal to 2, x of 2 can be written as 1 plus 2 into e power minus j 2 pi plus 3 into e power minus j 3 pi. This can be simplified as 1 plus 2 multiplied by 1 because e power minus j into 2 pi is equal to 1. Similarly, e power minus j into 3 pi is equal to minus 1. So 3 into e power minus j 3 pi can be written as minus 3. So x of 2 will be equal to 0. Similarly, we can show that for k equal to 3, x of 3 is equal to minus 1 minus 3j. From this, we see that the 4-point DFT x of k is equal to 6 comma minus 1 plus 3j comma 0 comma minus 1 minus 3j. For the given signal, we see that the 4-point DFT can be obtained as shown. Now, let us consider another problem as per which there is a signal x of n of length n and corresponding DFT implementation is obtained by FFT algorithm. There are some statements given as related to the FFT implementation. We need to find if these statements are correct or not. The number of multiplication for FFT implementation is equal to order of n into log n to the base 2. And the statement 2 is that FFT uses in-place computation and the statement 3 is that FFT is an approximation to DFT. We need to find which of these statements are correct. We know that in case of FFT implementation, the number of multiplication required is equal to order of n into log n to the base 2. So the statement 1 is correct. Also, we know that FFT uses in-place computations to save memory requirement. So the statement 2 is also correct. Also, FFT is an implementation of DFT and the output obtained here is in bit exact with DFT but not approximation to DFT. So the statement 3 is not correct. Now let us consider another problem as per which there is a signal x of n which is given as 1 comma minus 1 comma 2 comma 3 where the value of 1 corresponds to the instant n is equal to 0. If x of k is FFT implementation of x of n, we need to find x of 1. We know that FFT implementation is equivalent to getting we know that FFT implementation is mainly to get the DFT of the signal. So from this we can write that x of 1 is actually second coefficient in the DFT implementation. So this can be written as sigma n equal to 0 to n minus 1 x of n multiplied by e power minus j into 2 pi by n k n. Here k is equal to 1. Upon substituting different values for n is equal to 4 because the signal is of length 4, we see that x of 1 can be written as sigma n equal to 0 to 3 x of n multiplied by e power minus j pi by 2 n. So from this we see that the summation can be simplified as x of 0 plus x of 1 multiplied by e power minus j pi by 2 plus x of 2 multiplied by e power minus j pi plus x of 3 multiplied by e power minus j 3 pi by 2. Upon substituting for different values, we see that this is equal to 1 minus 1 multiplied by minus j, because e power minus j pi by 2 is equal to minus j, plus 2 multiplied by minus 1, because e power minus j pi is equal to minus 1, plus 3 multiplied by j, because e power minus j 3 pi by 2 is equal to j. Upon simplifying, we see that this is equal to minus 1 plus 4j. From this, we see that for the given signal, if x of k is the FFT implementation, x of 1 can be written as minus 1 plus 4j. Now, let us consider another problem as per which there is a sinusoidal signal at a frequency of 1 kHz. The signal is sampled at a sampling frequency of 1.5 kHz. Now, the sampled signal is passed through a LPF of cutoff frequency 800 Hz. We need to find the frequency of the output signal. As per the given problem, there is a sinusoid at frequency of 1 kHz. The same is sampled at 1.5 kHz. Now, the sample signal is passed through a low pass filter of cutoff frequency 800 Hz. We need to find the frequency of the output sinusoid. We know that the Fourier transform of a sinusoid is contains two impulses at frequencies 1 kHz. Here the frequency is in kilohertz for the frequency spectrum drawn. Now, this signal is sampled at a frequency of 1.5 kilohertz, because of which we will see the repetitions of the frequency spectrum shown, and the repetitions are centered at 1.5 kilohertz. So, this is the frequency spectrum which is centered at 0 kilohertz. Now, there will be another spectrum which is centered at 1.5 kilohertz, because of which we see that there are two impulses at zero point 0.5 and 2.5 kilohertz. Similarly, corresponding to the frequency spectrum corresponding to the centering at minus 1.5, we see the impulses at minus 2.5 and minus zero point 0.5, and so on. This repetition would repeat. Please note that whatever we have drawn here is the frequency spectrum of the sample signal. Now, the sample signal is passed through a low pass filter of cutoff frequency zero point 0.8 kHz. So, the frequency spectrum of low pass filter, which is centered at 0, is as shown. Now, because of the filtering in time domain, it is equal to multiplication in frequency domain. We see that the frequency representation will have two impulses at zero point 0.5 kilohertz. From this, we see that the output is a sinusoid of frequency equal to zero point 0.5 kilohertz. So from this we can see that the output of the low pass filter is a sinusoid of frequency zero point 0.5 kilohertz. Now let us consider another problem as per which there is a low pass filter of cutoff frequency 30 Hz. It is cascaded with a high pass filter of cutoff frequency 20 Hz. We need to find the nature of the resultant filter, that is whether it is a low pass or high pass or band pass or band stop filter. From this we can see that the low pass filter with a cutoff frequency of omega c will be as shown, and the high pass frequency with a cutoff frequency of 20 Hz would be as shown. Due to the cascade connection, we see that the resultant filter will be as shown. It is a band pass filter passing the frequencies in the range of 20 Hz to 30 Hz. So from this we see that the resultant filter is a band pass filter of bandwidth 10 Hz. Now let us consider another problem, as per which the direct form implementation of a system LTI system with system function as 1 plus 2z inverse, sorry, 1 plus 3z inverse plus z power minus 2 divided by 1 plus 0.75 z inverse minus z power minus 2. Please note that this LTI system is causal. Also, the direct form implementation of the LTI system is as shown. It will have two delay elements, Z inverse and Z inverse, and it has the branches each of gain A, B, C, and D. We need to find the gains of the branches, that is A, B, C, and D. We see that from the given implementation, the signal at the point capital A can be written as, okay, before that let us assume that the signal at the point capital A, capital B, and capital C as capital A of n, capital B of n, and capital C of n. From this we see that A of n, capital A of n is equal to x of n plus A into B, B of n minus 1 plus B into B of n minus 2. Also we know that the signal B of n can be written as A of n. Similarly, C of n can be written as B of n plus C into B of n minus 1 plus D into B of n minus 2. From this we see that the output Y of n is equal to C of n, which is equal to, fuck off. Now let us consider another problem, as per which there is a signal x of t which has a bandwidth of fh, and there is a derived signal y of t which is written as x of t by 2 plus x of t minus x of 2t. We need to find the Nyquist sampling frequency of y of t. From the given signal y of t, we see that x of t by 2 is a expanded version in time domain. We know that expansion in time domain is equivalent to compression in frequency domain. From this, we can say that the signal x of t by 2 has a bandwidth of 2ft. Similarly, we can say that the signal x of 2t has a bandwidth of f by 2, as, sorry, x of t by 2 has a bandwidth of f by 2. Similarly, we can say that x of 2t has a bandwidth of 2f, as x of 2t is equivalent to compressing the signal x of t in time domain, so expansion in frequency domain. Also, it is given that x of t has a bandwidth of f. From this, we can say that the signal y of t has a bandwidth of 2f. So the Nyquist sampling frequency of y of t is equal to 2 into 2f, that is equal to 4f. Now let us consider another problem, as per which it is given that there is an all pass filter which has a pole at 2 into e power j pi by 4. There are two statements given as related to the all pass filter. The state, as per statement 1, there is a 0 at half into e power j pi by 4, and there is a pole at 2 into e power minus j pi by 4. We need to find the correctness of these two statements. We know that if there is an all pass filter which has a pole at p, it will have a 0 at 1 by p star, because poles and zeros form conjugate reciprocal pairs. So the 0 can be written as 1 by 2 into e power minus j by 4, which can be simplified as half e power j pi by 4. From this, we can say that the statement 1 is correct. Also, if there is a pole at p for an all pass filter, we can't comment anything about another pole p2 as related to the all pass filter, as it is not given if the all pass filter has real impulse response. From this, we can say that we can't surely say if there is a pole at 2 into 2 into e power j pi to e power minus j pi by 4. From this, the statement 2 is wrong. So out of the given two statements, the statement 1 is correct and the statement 2 is wrong. Now, let us consider another problem, as per which there is a LTI system which is causal and whose filter structure implementation is as shown in the figure. There is an input of x of n to the filter structure, and the structure gives an output of y of n, and there are some branches with the gains of a, c, and minus b, and they have a delay of z inverse. We need to find the system impulse, we need to find the impulse response of this LTI system if the system is causal. From the given filter structure, we see that the intermediate output, that is marked as A of n, can be written as A of n is equal to A into x of n minus B into x of n minus 1. Also, from this we can write that y of n is equal to A of n, sorry, A of n would be equal to minus b into x of n minus 1 plus c into y of n minus 1. Also, we know that y of n is equal to A of n from the given structure. From this, by taking Z transform on both sides for the obtained LCCDE, we see that y of z is equal to A into x of z minus b z inverse x of z plus c z inverse y of z. Upon simplifying the given above equation for h of z, which is equal to y of z divided by x of z, we see that The impulse response h of z can be written as a minus b z inverse divided by 1 minus c z inverse. As the system is causal, the impulse response of the LTI system can be obtained by rewriting h of z as shown. That is, h of z is equal to a multiplied by 1 minus c z inverse minus b multiplied by z inverse divided by 1 minus c z inverse. We know that the inverse z transform of 1 by c 1 minus c z inverse is equal to c power n into u of n as the system is causal. Similarly, the inverse z transform of z inverse by 1 minus c z inverse is equal to c power n minus 1 multiplied by u of n minus 1. From this, we can write the impulse response of the LTI system as h of n is equal to a into c power n into u of n minus b into c power n minus 1 multiplied by u of n minus 1. So whatever we got is the impulse response of the causal LTI system with the given filter structure. Now let us consider another problem as per which it is given that there is a signal x of t which is in the frequency range of 5 kHz and 10 kHz. We need to find which of the given frequencies is surely not present in x power 4 of t. The options given are 7.5 kHz, 14 kHz, 18.5 kHz, and 45 kHz. Please note that here the answer could be more than 1. We know that x power 4 of t in frequency domain can be written as Fourier transform of x power 4 of t is equal to x of j omega convolved with x of j omega convolved with x of j omega convolved with x of j omega. This is because of the reason that multiplication in time domain is equivalent to convolution in frequency domain. So from this, Fourier transform of x power 4 of t starts from 5 into 4 that is equal to 20 kilohertz and is of length L is equal to 5 into 4 that is equal to 20 kilohertz. So from this we can say that Fourier transform of x power 4 of t is in the range of 20 kilohertz to 40 kilohertz in the frequency domain. From this we can say that all the options given would not definitely lie in the frequency representation of x power 4 of t. Now let us consider another problem as per which there is a signal x of t which needs to be sampled at 5000 samples per second for alias free reconstruction. It is given that there is a signal x of t which is written as a square of t. We need to find the Nyquist sampling rate of this signal. From the given data, we see that the signal S of t is at a frequency of 2.5 kHz. From this, we can say that x of t is equal to s square of t has a bandwidth of fx is equal to 5 kHz. This is because of the reason that x of t in the frequency domain is equivalent to s of j omega convolved with s of j omega. This is because multiplication in time domain is equivalent to convolution in frequency domain. From this we see that the signal x of t has a frequency of 5 kHz. So the sampling frequency of x of t for alias free reconstruction is 2 into fx, that is equal to 10 kilo H. Now let us consider another problem, as per which it is given that there is a all pass system h of z whose system function is given as z inverse minus 3 phase 30 degrees divided by 1 minus 3 phase minus 30 degrees z inverse. It is given that this all pass filter has complex impulse response. It is required that the given filter needs to be made all pass filter with real impulse response, for which we need to connect another system in cascade with h of z. We need to find the system function of g of z which needs to be connected in cascade with h of z to get the final filter as a all pass filter with real impulse response. We know that for real impulse response, the overall system function, that is h of z multiplied by g of z, should have the zeros as complex conjugates and poles as complex conjugates. From this, we can say that the overall impulse response, overall system function should be z inverse minus 3 phase 30 multiplied by z inverse minus 3 phase minus 30 degrees divided by 1 minus 3 phase minus 30 degrees z inverse multiplied by 1 minus 3 phase 30 degrees z inverse, because in this case zeros would be complex conjugate and poles would be complex conjugates. Also please note that zeros and poles will form a conjugate reciprocal pair, because of which the overall system O of z would be all pass. So the system that needs to be corrected in cascade is G of Z, which is highlighted as shown. Now let us consider another problem, as per which there is a signal g of t given as cos square of cos of 200 pi t multiplied by cos of 800 pi t. We need to find the Nyquist sampling rate of g of t. We know that the signal g of t can be simplified as half multiplied by 2 cos 800 pi t cos 200 pi t. We know that 2 cos A cos B is equal to cos of A plus B plus cos of A minus B. From this, g of t can be written as half multiplied by cos of 1000 pi t plus cos of 600 pi t. From this, we can say that the Nyquist sampling frequency, the bandwidth of g of t is equal to 500 Hz. From this, the Nyquist sampling frequency of g of t is equal to 1000 Hz, which is 2 times fg. So the Nyquist sampling frequency of given signal is 1000 Hz. Now let us consider another problem, as per which it is given that the system function of a LTI system is given as h of z is equal to z inverse minus 2 phase 30 degrees divided by 1 minus a z inverse. There are two statements given as related to h of z. The statement 1 says that the system is all pass filter if a is equal to 2 at a phase of 30 degrees, and as per the statement 2, the, the system is minimum phase if a is equal to 1 by 2 phase 30 degrees and causal. We know that for the given h of z, the system is all pass if poles and zeros form conjugate reciprocal pair. For this condition to be satisfied, P should be equal to 1 by Z star, that implies A should be equal to 2 at a phase of minus 30 degrees. From this, we can say that the statement 1 is not correct. Also, we can say that for the given system function h of z, if it is causal, it would be minimum phase if poles and zero are inside unit circle. From the given data, we see that the 0 is at 1 by 2 at a phase of minus 30 degrees. It is at inside unit circle, and the pole P is equal to A, which is half phase 30 degrees, which is also inside unit circle. From this, we can say that the given system would be minimum phase if it is causal and A is equal to half phase 30 degrees. From this, we see that the statement 2 is correct. For, so, for the given system function, we see that the statement 1 is wrong and the statement 2 is correct.